Section. Introduction. We're going to delve into the fascinating world of large transformer-based models. These models are capable of some truly impressive feats, performing at a superhuman level on a wide range of language and reasoning tasks. However, they're not perfect. They can sometimes fail in surprising ways, especially on tasks that are closely related to the ones they excel at. As these models continue to evolve and their capabilities expand, it's becoming increasingly important to understand why they fail and how we can control these failures. Several techniques have been developed to fine-tune these models. One particularly effective approach combines reinforcement learning with automated red teaming. This allows us to shape the behavior of large models, generate and curate high-quality datasets, and build powerful reward models that can describe complex, natural language concepts of reward, such as correctness or safety. These techniques have significantly improved the quality of models, especially in guiding their behavior towards becoming better interactive assistants and instruction-following machines. However, there are still significant gaps in our understanding of model failures. It's challenging to fully characterize these failures. We want our models to be aligned, but defining what alignment means is practically impossible. It could require additional complexity, like special casing, localization, human overseers, and more. In the worst-case scenario, it could be as difficult as defining morality, a task that even humans can't agree on. Because of the complexity of the problem, we've decided to focus on a specific aspect: arithmetic questions posed in natural language. We're asking, can these advanced models perform arithmetic correctly, even when adversaries are trying to lead them astray? This approach allows us to avoid the challenge of defining a complex or controversial concept of alignment. Instead, we simply require the model to answer arithmetic questions correctly. However, this is sometimes easier said than done. Solving arithmetic problems also exposes the breadth and complexity of natural language, providing a rich area for potential attacks. For instance, we wouldn't want a language model handling sensitive financial information to make basic arithmetic errors. More broadly, natural language arithmetic is a problem where it's easy to verify good behavior, but fully identifying all potential attack vectors is a useful microcosm of the larger problem of alignment. In our research, we've developed a new testbed for exploring alignment techniques, attacks, and mitigations. We've also created a simple algorithm for generating rich adversarial attacks that can transfer across model families and reliably cause non-hardened models to make arithmetic errors. We've analyzed performance changes during training, including on transfer to out-of-distribution model attacks. We've also evaluated the effectiveness of mitigation strategies for agentic loops, such as allowing models to revise their answers. Our findings suggest that it's possible to significantly mitigate attacks that cause inappropriate model behavior for arithmetic. However, we can't completely eliminate this vulnerability. Our work builds on previous research that explored the trade-off between helpfulness and harmlessness in model alignment. Other studies have shown that language models with prompting capabilities can be asked to iteratively rate and adjust their reasoning traces and outputs according to some notion of goodness. It's also been demonstrated that powerful language models can capture human preferences and act as the value function of a reinforcement learning procedure, with minimal human inputs. Adversarial attacks on neural networks have been extensively studied. For computer vision models, small perturbations that are imperceptible to humans can lead to adversary-controlled outputs. These perturbations are typically generated in a white box manner, using access to model gradients. However, attacking language models is more challenging due to the discrete input space and the non-differentiable output sampling process. For multimodal language models, adversarial perturbations in the image space have been shown to successfully perturb the outputs in language space. This can lead to harmful generations from the model without requiring an attack through language space. Attacking, or defending, a pure language model remains a challenging task in either a black box or white box setting. There are also black box methods for attacking language models, which do not require access to model gradients. These methods can be used to elicit outputs that violate some constraint on the language model behavior. Our work also complements ongoing research into the phenomenon of sycophancy, where models are likely to repeat erroneous statements made confidently by users. We expect that research into reducing sycophancy will also reduce the corresponding adversarial attack surfaces we report in this study. Section Summary. large transformer-based models have shown both impressive performance and unexpected failures in various natural language and reasoning tasks. To better understand and control these failures, techniques like RL, H, AI, F, and automated red teaming have been used to shape model behavior. In this study, the focus is on aligning models to correctly answer arithmetic questions, which serves as a microcosm of the broader problem of alignment. The authors introduce a testbed for exploring alignment techniques, provide an algorithm for generating adversarial attacks, analyze performance changes during training, and find that while attacks can be mitigated, complete removal of vulnerabilities is not possible. Section: Comparison with prior art. In this study, we've developed a search method that can consistently find ways to exploit a model in a restricted environment, even without direct access to the model's gradients or embeddings. This is similar to previous works that also depend on minimal feedback from the model. Our method is unique in that it can generate inputs that lead to specific string outputs, or inversions, or that break the model's general code of conduct. We've also introduced two simple strategies to counter these attacks. The first is to strengthen the model using feedback from AI, and the second is to allow the model to revise its own responses. These strategies significantly reduce the effectiveness of our attack search method, making the model more resistant to these attacks without needing human feedback on each generation. However, we haven't tested these strategies against white box attack methods, as that's beyond the scope of this paper. There's some debate about whether allowing a model to revise its answers is a good or appropriate intervention, but we believe it can be useful for alignment purposes. We've also developed many techniques for generating specific, dangerous continuations from models, such as jailbreaking, soft prompt tuning, and even directly optimizing tokens. While methods that use gradients and have direct access to the model can result in more powerful attacks, these attacks are often not representative of typical user interactions and resemble the noisy adversarial vulnerabilities that have plagued image-based models for years. Instead, we focus on creating attacks that are semantically understandable and indicative of more serious failures. All the attacks used in this study for training were generated using an algorithm we call prompt inversion rejection sampling, PIRS. In PIRS, an attacker model generates attacks that will guide a defender model to generate content that breaks the desired behavior. The attacker model generates an attack by creating a string that will be part of the context for the defender model's generation. Ideally, we want to invert the probability that the defender model generates bad text given the context generated by the attacker model. However, large models are not easily invertible, so this is usually difficult. We can sometimes use large models to directly perform this inversion by using a specific prompt. For arithmetic problems, we use such a prompt to have the model generate arguments that would make it answer arithmetic problems incorrectly. For example, we might instruct the model to generate an argument for why it would say that 2 plus 2 equals 5. We then have an additional evaluation prompt to determine if the attack was successful. In arithmetic, we check to see whether the defender model is successfully guided to answer the arithmetic question incorrectly. Thus, the process of prompt inversion rejection sampling goes as follows. 1. Use the attacker model to sample candidate attacks using the attack prompt template. 2. Use the defender model to evaluate candidate attack prompts with the evaluation prompt template. 3. If the defender model outputs the desired, incorrect, answer, accept. Otherwise, reject and go back to step 1. We use this procedure, with different templates as described in the next section, to generate a dataset of viable attacks for use in adversarial training. Section Summary. In this section, the authors compare their search procedure with prior art and demonstrate that their method can produce successful attacks on a model without white box access. They also introduce two mitigation strategies to reduce these attacks, but note that testing them on white box attack strategies is beyond the scope of the paper. The authors focus on generating semantically understandable attacks and describe their prompt inversion rejection sampling (PIRS) algorithm, which generates attacks by having a red language model steer a blue language model to produce undesirable outputs. Section: Attack Success Probability. In this section, we're going to explore how the success of an attack is influenced by the characteristics of the red, the attacker, and blue, the target, language models. We'll be using prompts generated through a method called prompt inversion rejection sampling. We've created several different prompts that can be used to launch attacks, and these prompts can be adjusted depending on the size of the error we want to induce. For instance, if we use the prompt 2 plus 2 equals 5, the error is 1. In our analysis, we're focusing on simple arithmetic involving one-digit numbers, with the target error randomly chosen between 1 and 10. Each attack is independently and randomly sampled for adding two numbers between 1 and 10. We've found that the success rate of an attack doesn't necessarily increase as the blue models get larger. We've also noticed that the success rate of an attack tends to increase as the targeted error size increases. We've also been keeping an eye on steerable errors, which are attacks that successfully guide a model towards a specific incorrect answer. Interestingly, steering a model towards a specific wrong answer is almost as easy as getting it to make a mistake in the first place. Next, we'll look at how the success of an attack depends on the red and blue models. We're only going to consider creative_v2 attacks in this section. We've found that attacks generated by GPT-4 using prompt inversion rejection sampling are the most effective against all models, and that the Claude family of models is the most resistant. Providing a helpful system directive has mixed results. In some cases, it makes models worse at finding attacks, but it also makes them more resilient to attacks. We've also been studying the effects of training large models to resist the attacks we've discussed. This involves two stages. The red model generates a dataset of attacks, and the blue model is fine-tuned to minimize a reward function that penalizes generations that violate desired behavior. We've used a method called proximal policy optimization, PPO, for fine-tuning. The choice of hyperparameters for PPO can greatly affect training time and performance. After selecting the hyperparameters, we kept them constant for all other experiments. We've also been looking at how training and validation performance change with dataset size. We didn't see a significant change in validation performance on held-out adversarial examples as the dataset size increased. Finally, we've been examining the effect of varying the proportion of the dataset that is made up of true negatives. A true negative is a training example where the red model was instructed to generate an example that would guide a model to the incorrect answer. We found that the model doesn't learn to defeat adversarial examples until later in training unless the true negative percentage is above a certain threshold. However, once this threshold is reached, validation performance is similar. This suggests that training on semantically rich corruptions of data can be a powerful technique for improving robustness, even when the majority of data is typical. Section Summary. In this section, the authors analyze the success of attacks on language models based on various factors such as model size and error magnitude. They find that larger models do not necessarily become more robust against attacks, and that attack success generally increases with the targeted error magnitude. Additionally, they observe that steering the model towards a specific wrong answer is almost as easy as getting it to misbehave in general. The authors also investigate the effectiveness of attacks against different models and the impact of adversarial hardening on model resilience. They further explore the effects of dataset size and the composition of true negatives on training and validation performance. Section: Evaluation Metrics. We've used a variety of evaluation tasks to assess our model's performance during fine-tuning. One of these tasks is sequence copying, where we test the model's ability to copy different types of sequences, such as random ASCII characters, random digits, and arithmetic problems. We've found that the model can copy sequences well even after multiple repetitions, maintaining a near-perfect performance. However, when the model is only given two examples to copy from, its performance starts to decline. Interestingly, copying random equations seems to be a good early indicator of the model's progress in fine-tuning. We've also developed a dataset of evaluation prompts to understand how the wording of the prompt affects the model's performance. These prompts ask the model to add two numbers in different ways. As the model is fine-tuned and learns to answer arithmetic questions correctly, its performance on these prompts improves. However, there's some ambiguity in how the model should present the answer, which can affect its performance. For instance, early in the fine-tuning process, the model sometimes generates more arithmetic problems instead of providing the answer. We've also created arithmetic word problems to test the model's ability to perform arithmetic in natural language. These problems are generated by a large instruction-tuned model that creates random stories, each containing a sentence with a random number of a specific object. The model's performance on these problems doesn't change throughout training, even though some problems are harder than others. In addition to these arithmetic-specific evaluations, we've also monitored the model's performance on several other tasks in the Big Bench suite. Most tasks see modest decreases or plateaus in behavior, with the exception of the emoji_movie and strategy_ka tasks, which see significantly reduced scores during fine-tuning on adversarial arithmetic tasks. Finally, we've conducted out-of-distribution attacks to better understand the model's performance before and after fine-tuning. These attacks are designed to make the model make a specific error when adding two numbers. All attacks work with extremely high probability on unhardened models, and all attacks are diminished in effectiveness after hardening, with the exception of the philosophize attack. This suggests that adversarial training on PIRS-generated datasets does provide out-of-distribution mitigation for other arithmetic-like attack types not seen during training, though there remains room to improve. Section Summary. The evaluation metrics used in this study include sequence copying tasks, random templating tasks, procedural word problems, auxiliary tasks, and out-of-distribution attacks. The sequence copying tasks show that the models perform well when copying sequences with more than two examples, but struggle with only two examples. The random templating tasks demonstrate that the wording of the evaluation prompt affects the model's performance. The procedural word problems assess the model's ability to perform arithmetic in natural language, and the auxiliary tasks evaluate performance on various tasks in the Big Bench suite. Finally, the out-of-distribution attacks highlight the effectiveness of adversarial training in mitigating certain attack types. Section: Context Overload. In our study, we explored a type of attack we call context overload. In this attack, we added a variable, which was the number of times a false equation, like 2 plus 2 equals 5, was repeated within a given context. We kept this number constant for our experiment. To understand the impact of repeating a false equation, we used a specific template. In this template, we looked at how the number of repetitions of a false equation, like z equals 10n, and the choice of suffix influenced the model's likelihood of responding with 4 versus 10. As expected, the base model was quickly swayed and gave the wrong answer with a higher probability, shown by a negative value on the plot. However, the hardened model resisted the false information until thousands of copies of the false equation were present in the context. We also examined how the model's performance varied when faced with different suffixes in the attack. While the hardened model generally resisted attacks better, a carefully chosen suffix could still undermine it. We used two different suffixes to try to understand how the model might be overly focused on the specific prompts it was trained on. However, it was hard to draw a clear conclusion. In some cases, changing the suffix made the attack more successful, while in others it made the attack less effective. We also explored agentic mitigations in attacks, where the model is given an additional mechanism and doesn't just behave in a feed-forward manner. We implemented a method where another model was prompted to revise the first model's output, based on a set of overriding instructions we call a constitution. We used a powerful model, POM2L, to perform the revision task. This approach nearly closed the gap between a raw, untuned model and our attack-hardened model. However, the success of this method depends on the revision model's ability to accurately judge and revise the generated text. We found that even unhardened models performed almost as well as hardened models when used in this configuration. This suggests that further investigation into interventions like this could be a good alternative to hardening by fine-tuning. We proposed adversarial arithmetic as a way to explore alignment and capability failures in large models. We showed that existing models are vulnerable to attacks in this setting, and we developed a simple algorithm that produces reliable attacks. These attacks can be directed to make the model give a specific wrong answer. We found that both RL fine-tuning and constitution checking can effectively mitigate these vulnerabilities, but neither method is perfect. There are still many open questions, such as why models are so sensitive to subtle changes in the attack prompt, or why different choices in the adversarial training procedure lead to different evaluation metrics. We hope that our work will highlight some of the current challenges and provide a simple way to explore solutions.